Hello. In this video we're going to be talking about the fundamental theorem of calculus. And so there are two parts to this, but both of them start noting that we have some function f that's continuous over an interval from a to b. And so the first part of this says that we can define some function g so that it's the same as the integral of f of t from a to x of dt over the interval from a to b. So if you notice that g of x, when you input an x, that gives you the top part of the integral, so where you go from a to somewhere within a to b. And so what this tells us, that function, we also know that that function is continuous over a to b as well. It's also differentiable over that interval, and what the fundamental theorem of calculus is going to tell us is that the derivative of g is the same as the function f. And so what we're learning is basically that the function f, when we're asked to do the integral, when we're asked to integrate, it goes backwards and it's the antiderivative. So the function f being integrated just means we would do the antiderivative of the function. So number two, the part two, looking at this integral of the function f from a to b, well, the capital F is going to be our antiderivative. And so if we want to evaluate this integral from a to b, then we would find the antiderivative of f, and so that would be our capital F. Then we'll plug in the value of b and subtract the value, that antiderivative, with the plugged in value of a. So let's use this information and do some examples. So in example 1, we want to find the derivative of our function g of x. And g of x is the same as the integral of our square root of 1 plus t squared from 0 to x. And so this looks just like part 1 of our fundamental theorem of calculus. We have to make a note that 1 plus t squared is continuous. And it's definitely continuous from 0 on to wherever x is taking it. And so because of that, because of part 1, we know that g prime of x, which is the derivative of g, is going to be the same as what we're being told to do the integral of. So it's going to be the same as the square root of 1 plus, and instead of t squared, 1 plus x squared. And so that's the derivative. Again, an integral is an antiderivative, so doing the derivative of g should just get me what we're doing the integral of in the other part. In number 2, we're evaluating the integral of x squared from -2 to 1. Again, we can note that x squared is continuous. It's continuous everywhere. It's a nice little parabola. And so from part 2, we want to do the antiderivative of x squared. So f of x is, well, first note that f of x, the little f of x, is x squared. So the antiderivative of this, we raise our exponent by 1, and we divide that by what's out front. So if I were to take 3 times 1/3, I'd be back to 1, lower my exponent to be x squared. And so that's the big F of x. And so the evaluation of this is going to be big F of 1 minus big F of -2. And so we're going to plug these numbers in. And so big F of 1 is 1/3 times 1 to the third minus 1/3 times -2 to the third. Well, 1 to the third is 1 times 1/3 is 1/3 minus -2 to the third is -8 times 1/3 is -8/3. And so our minus and negative will become plus the positive. And so 1/3 plus 8/3 gives us 9/3. which results in 3. And so the integral from negative 2 to 1 of x squared results in a value of 3. And we talked about how integrals are areas. So to draw this figure, we're looking at x squared from x equals 1 to negative 2. And so this space right here sums up to be a total of 3. Okay, and so that's your introduction to the fundamental theorem of calculus. We'll certainly do more of this in class later, so for now we are done.